In this lecture, I'll going to explain this beautiful formula, which is decomposition of pseudo-metric space using open poles and intersections. It's beautiful for many reasons. I'll explain them. The first thing, I'll prove this formula using 2 or 3 steps. The first step is to explain and analyze this part, which is the intersections of open poles. Firstly, the open poles or neighborhoods be indexed by epsilon n. It's a subset of pseudo-metric space X hat. It's a subspace of X. Epsilon n is functions from natural numbers to R for all n natural number. So with some special analytical condition, which is the infinium of epsilon n of the natural numbers and is equal to 0. So before we will start in the proof and details, I need to explain the neighborhoods and these functions, epsilon n. Epsilon n is a function from n to r for all n natural numbers and with some special analytical condition. This condition is a very beautiful condition because this formula is held if and only if this condition exists. This formula is held if and only if this condition exists. So we can say in other words, x is is equal to if and only if existence of this window is only the existence of infinium. So what I need to explain now, the definition of neighborhoods. B a epsilon n is equal or defined to be all elements in X such that the distance between X and A is little than epsilon n. So now that is the definition of open poles in pseudo-metric space. Of course, the neighborhoods are subsets of X for all n natural number. Now, what I mean by the intersection of these neighborhoods or open poles, not something that this before I explain the intersections, I'm going to explain common quotient and the equivalence classes in this pseudo-metric space. Note something beautiful, which is the kernel of D. What I mean by kernel of D? The kernel of these all pairs x, y, and x such that D hat of x and y are equal to 0. That is the kernel of D. So I I'm going to define equivalence relation between x and y. X equivalence y if and only if dxy is equal to 0. So this is the equivalence relation. Of course, it's equivalence relation because the metric is equivalence relation where the metric is equal to 0. The metric is equivalence relation because it's symmetric, transitive, reflexive, and that is famous and formal conditions of ordinary metric space. Now, I'll define the equivalence class A. It's just equal to all elements x and x, where there is equivalence relation between x and a, which means that it's the set of all members x in pseudo-metric space where or such that the metric of x and a is equal to 0. So, of course, equivalence class A is a member or elements in Kolmogorov quotient for pseudo-metric space, which is equal to all equivalence classes for all A metric pseudo-metric space X. Now, after defining equivalence classes and Kolmogorov quotient, I'm going to find the intersections of open pole. In fact, the intersection of open poles in pseudo-metric space is equal to equivalence class A here. The intersection of open pole and the open pole of all the open poles around A is equal to the equivalence class of A. So the intersection is element of Kolmogorov quotient. I need to prove this. Let's prove it. Now, firstly, I'll prove that the intersection, is a subset of the equivalence class. I'll prove this. So firstly, I'll suppose that I have element for all element x in intersection that means what? That leads us to conclude that x is element of b, a, epsilon, n for all n natural number. So that leads us to conclude that x, by this definition, that leads us to conclude that metric of x and a is little than, greater than or equal to 0, and little than epsilon, and that is for all n natural numbers. Now, I'll take the infinium for both sides of the inequality. I get here infinium is equal here to 0. So, of course, the metric cannot be little little than 0. It must be equal or greater than 0. So it's already little than 0 and greater or equal to 0. So that means d of x and a is equal to 0, which means that x is element of equivalence class A by the definition. I wrote it before here. So that leads to conclude that x is element of equivalence class A because the definition is hold on x. I'll write it here. A, which is equal to 0. This is a very important definition, and the definition of Kolmogorov quotient is the set of all equivalence classes such that for all A and X. So by this definition above, we conclude that X is element of equivalence class of A. We'll start the proof from all elements of the intersection and conclude that all elements in the intersection belong to equivalence class A. That means logically that X is the intersection of neighborhoods epsilon n of A, epsilon n of A for all natural numbers, and is a subset of equivalence class A. So now that is the first most important result. I found it. I write it here. The intersection of open balls for all natural numbers n is subset of A. Now, the inverse direction. I'll prove that the intersection, A is subset of the intersection. Now, to prove this, let X be element of equivalence class A. Now, let X be element of equivalence class A of A. That leads us to conclude that d of x and A is equal to 0 for all x in equivalence class A by the definition above. Now, let's epsilon n greater than 0. Because epsilon n is greater than 0, I conclude that d of xa is equal to 0 and little than epsilon n. Now, what is this? This is a definition, formal definition of open poles. That means x is belong to open pole. So x is element of open pole of A by indexed by epsilon n. In this assumption, I take epsilon n greater than 0, of course, for all n natural numbers. So I get that x is belong to the open pole or neighborhoods of A around A for all epsilon n for all which belong to the intersection. So X is belong to the intersection of open poles. We'll start the proof by taking all elements in equivalence class of A, and we find that all elements X are belong to the intersection of open poles. So we can conclude voicely that equivalence class of A is a subset of the intersection. That is the second result, that A is a subset of the intersection. Now, since A is a subset of the intersection, and at the same time, the intersection is a subset of equivalence class A. That leads us to conclude that the intersection is equal to the equivalence class for all A in X. That means the intersections are elements or members in Kolmogorov quotient, so we can define Kolmogorov quotient. I'll replace this two results in one result. I can say that the intersection is already equal to A, of course, for all A in metric space. So now we can define Kolmogorov quotient to be the set of all intersections by this result, of course, for all A. So the first result that I wrote it and conclude is that the intersection of open poles around A, or around some point in pseudo-metric space, is equal to the equivalence class of this point. So I wrote before that the intersection of epsilon A, epsilon n is equal to the equivalence class of A for all A in X. That was the first result. Now I'm going to prove that the intersection of all intersections of open poles, for all open poles, I mean for all elements A in X, is equal to phi null set. It is interesting results to conclude. Now I'm going to prove this by contradiction. Now let's X and Y, or let's let alpha and beta be elements of X. We need to prove by contradiction that the intersection over all elements in X for all intersections of open poles around every point of pseudo-metric space is equal to 5. This formula is useful to us for a very interesting reason. I'll explain it after prove this formula. So firstly, let alpha and beta be elements of X. I need to prove that, or I need to suppose that intersection of open pole of alpha, epsilon n, the intersection of b, beta of epsilon n is not equal to phi, doesn't equal to phi. So I need to suppose now that Z is element of this intersection, of this part of equation. Let Z in X, where Z is element or belong to the first intersection, indexed by epsilon n for all n natural numbers, and at the same time Z is element of the intersection of all open poles around beta over all natural numbers. So Z must belong to the intersection of the first intersection and the second intersection. Now Z is element or belong to the first intersection. That means metric of Z and alpha is little than epsilon n for all natural numbers n. And at the same time, the metric of Z and beta is little than epsilon n also for all n natural numbers. Now that's, I'll get to use triangle inequality to find the metric of alpha and beta. The metric of alpha and beta is little than or equal to the metric of alpha and Z plus metric of beta and Z. This part is equal, it's of course little than epsilon and it's equal to 0, and this part is also equal to 0. So d of alpha beta is little or equal to 0 plus 0. So I have 0 here. The metric cannot be little than 0, so it's 0. The metric of alpha beta is equal to 0. That means alpha is belong to the intersection of b beta epsilon n, and at the same time beta is belong to the intersection of open poles and alpha, which means immediately that the equivalence class of alpha is equal to equivalence class. I review the proof. Okay, so the equivalence class of alpha is equivalence class for beta is equal to equivalence class of beta, which is contradiction to the first assumption that they are distinct, they are not equal together, of course. So this is a contradiction there. So the intersection here is equal to 0. Equal to null set. That is the final result. So we can say that this is whole. Always it's whole. So this is the second result. I'm going to write it here. So Now must recall the formula, the main formula, which is X pseudo-geometric space is equal to the disjoint union equivalency classes here, common of quotients, the intersections of all natural numbers for epsilon A, epsilon N. So this is the main formula. Now, by this and this, by these two results, we need to conclude this formula. We already find this part, which is the intersection of all poles, which is equal to the equivalency classes. So we have ordinary decomposition of pseudo-geometric space. It's just ordinary decomposition. I mean that since by the second result, since that the intersection of all intersections is equal to phi, so that means the equivalency classes are distinct from each other. That means the union of all equivalency classes over X is already equal to X. That is trivial result. Honestly, it's a trivial result. But we replaced the symbol of the union by the disjoint union, which is right as this way. So the disjoint union of all equivalency classes is equal to the pseudo-geometric space X. Now, of course, we can say I am going to replace this equivalency class by this form, intersection, which is equal to X. And the proof is complete. Now, what is the geometrical interpretation for this formula, which I proved it before? Imagine that I have pseudo-geometric space. Call it X. I have a pseudo-geometric space. Now, let us to take some point here. A inside the pseudo-geometric space. Now, I'm going to take poles around A. Now, let's take this is sequence, circles, square. So the first square has a radio. It's I have here. That is epsilon 1. That is epsilon 2. Epsilon 3. Epsilon 4. Epsilon 5, and so on. The number of open poles is infinite. I have infinite number of open poles, so I have a lot of circles around some points. I have a question now. Is there any common factor between all of these squares around A, now that this is A, it's clear, inside the pseudo space, there is a common factor, of course, which is A itself, and it's a common factor between all of these squares. So every green square is open pole. Epsilon of A, epsilon 1. That is the greatest square is B. It says B epsilon next B sub epsilon 1 of A, which is equal to the supremium of all open poles. Okay. Of course. Now, the same thing with epsilon 2. Epsilon open pole indexed by epsilon 2 is a subset of B1 epsilon 1. I write a sequence here. B of A epsilon 1, B A epsilon 2, B. We have a sequence of circles around A. And it is here. B, A, and epsilon N. When, so we will get to infinity. I write of epsilon sub 0. Note that it's very interesting information that infinium of epsilon for all n is equal to epsilon sub equal to the epsilon of sub 0 sub infinity, which is equal to 0, which is equal to the limit and epsilon n. Now, I have a sequence of open poles. The intersection of all these open poles equal to the set, I mean the intersection of all of these squares, consecutive squares, sequence of squares or cycles or neighborhoods for all n, epsilon 1, epsilon 2, epsilon 3, epsilon n plus 1 to epsilon infinity is equal to the set of all elements of pseudo space such that the metric of x and a is equal to 0, where the distance between x, between the members of pseudo space and the central point a is equal to 0. So the intersection here is the common factor between all of these circles, the sequence of circles or open poles or neighborhoods, which is some points here. Now I have, that is circles around A. I have also circles around B. Here I have B. I have circles around B. I have C here. I have circles around C. I have D, and I have circles around D for all elements of pseudometric space. That is the geometrical interpretation. Here, these circles, these circles, these circles, these circles, all of these circles gives me, in the end, here, equivalence class of A. Equivalence class, here, equivalence class of A, equivalence class of B, equivalence class of D, equivalence class of C, and etc. Now, the union of all these equivalence classes gives me the pseudometric space itself, if you can see here. So, of course, for all members of all equivalence classes inside pseudometric space, which are members or elements in Kolmogorov coefficients of pseudometric space. Mathematics is not merely to be understood, it's to be felt. Mathematics is the poetry of abstraction. That is the reality of mathematics.